All right, so in this lecture, I'm going to be talking about measures of variability, which are going to give us information about the degree of spread, variation, or difference among the observations within a particular distribution. All right, so let's just start with the definition. Measures of variability provide numerical estimates of the amount of spread or difference that exists within a distribution of scores. So let's give an example. Let's just think about what does the variability of heights in the world look like? So as you can see in this example, I went online and I found out that the smallest person who ever lived in the world measured 1 foot 9.5 inches. It's pretty small, right? So just under 2 feet. The tallest person who is currently alive right now measures 8 feet and 3 inches. So there is nearly 6 foot difference, nearly the entire height of a very tall person between the smallest person and the tallest person who have ever lived. In between those, we also know we always have estimates of the average heights of men and women. So men on average are about 5'9", and women on average are about 5'3". So by looking at these numbers, we know a couple things. One is that we know what's the absolute outside range of the smallest and the tallest people right now. Certainly someone could be smaller, certainly there could be someone who eventually gets taller than that, but this is sort of the outer range, right? These are the extremes of those scores. And in the middle, we can expect to see quite a few people who are falling in that range of 5'3" to 5'9" based on gender. All right, so that gives us some information about what are the most frequent heights we can expect to see, what's the tallest person, what's the shortest person. We might even be able to kind of make some predictions about how many people we might see at a slightly higher end, like, what about people who are 6 feet tall? What about people who are, 4 feet tall, right? So we can kind of make some guesses about how many people will fall within these various ranges. But before we get into the specific metrics, let's talk a little bit let's just look at some examples of distribution shapes. So distributions can vary quite a bit in terms of their shape. We've already talked about skewed distributions, right, where we might have outliers in one direction or the other, and that's going to make the distributions sort of shift towards the right or shift towards the left. But we can also have distributions that are restricted, as in the example of this green one, where we have a dense population of scores towards the middle and very little range in terms of scores. One example of this might be if we were to look at IQ scores of people on college campuses. In order to go to college, you have to have at least an average and perhaps an above average IQ. So the range of IQ scores on a given college campus is going to be very restricted, right? It's going to be somewhere between 110 and 160, maybe 100 and 160. Whereas if we were to look at the distribution of IQs in the entire population, now we have the possibility of someone with an IQ of 40, and we have the possibility of someone with an IQ of 60, so that distribution is going to be much wider, right? It's going to actually follow more of a normal curve where it's a little flatter in the middle, and the tails are going to extend out further. On the other hand, we might have a distribution that's really flat in the center, meaning we have fewer people who are falling at the middle, more kind of falling a little bit further out from that center point, and we have some real extreme outliers in either end of the distribution. All right, so these characteristics, these distributions can take on a variety of different characteristics, and it's helpful to have a single value or a couple of values that help us to sort of get an estimate of how much spread is actually existing in our distributions. All right, so the first metric that we're going to look at is the range, and the advantage of the range is that it takes all of the possible scores into account. It basically gives us an estimate of the spread of scores from the highest value to the lowest value. And the formula for the range is the upper real limit for the highest score and subtracting the lower real limit for the lowest score. And it's represented as x upper real limit high minus x lower real limit low. So in this particular distribution of scores, I believe there's 16 of them, the lowest value is 7, the highest value is 25. Because this is whole numbers, right, our unit of measurement is 1, which means that 1/2 of the unit of measurement is 0.5. So our upper real limit is going to be 25.5 and our lower real limit is going to be 6.5. All right, so using our formula, 25.5 minus 6.5 gives us a range of 19, which essentially is telling us that the range of scores from highest to lowest is about 19 points. Now, as I said, one of the advantages of the range is that it takes all of the scores into account. And this is good if the scores don't vary a lot, or if there are what we call an extreme outlier. But let's just imagine this is maybe ages, maybe so ages, and we have people ranging in age from 7 to 25. There's not a wide distribution here, only about 19 years. But then all of a sudden we add somebody who's 55, right? They're 30 years older than the oldest person in this bunch. In this case, the upper real limit's 55.5. The lower real limit remains 6.5, but now our range is going to be 49 points. So that individual score is going to make the distribution or the spread of this distribution look way wider, even though it's sort of an unusual score, right? It's way outside kind of the typical scores that fall in the distribution, right? So when we think about means, for example, our mean would probably fall somewhere in the center range of around 13 or 14. Once we add this 55 in, it's going to pull that mean up, right? So it's having an impact both on our measure of central tendency, but also making the spread of scores look a lot bigger than it probably really is. In order to account for that, another estimate of variability is the interquartile range. And the interquartile range looks at the spread of scores just within the middle 50% of the distribution. So this way, it doesn't take into account all of the scores, but it also cannot be as dramatically affected by the inclusion of any outliers. So the interquartile range formula is the value at the 75th percentile or quarter 3 minus the value at the 25th percentile or quarter 1. So how do we do this? Well, essentially, in order to find these different quartiles, so you'll remember, right? 75th percentile, the value at which 75 of the scores fall at or below that value, and the 25th is the value where 25% of the scores fall at or below that value, right? So we find it by first splitting the distribution in half, and we call that quartile 2. So there are 16 scores in this distribution. I put this hash mark at the point such that there are 8 scores above it and 8 scores below it. If you recall, that actually is our median, right? It's the centermost score. So the median in this case would be probably 13.5 because our quartile 2 or our median falls in between the values 13 and 14. Now, in order to find quarter 1, we're going to split the lower half of the distribution in half so that there are 4 scores below it and 4 scores above it. And so here's our quartile 1. And as a result of that, since we have 11 on either side, we know that quartile 1 is equal to 11. Okay, so in order to find quartile 3, we're going to do the same thing. In this case, we're going to be looking at the upper half of the distribution. So we're going to put a hash mark that divides it in half. So there are 4 scores below, 4 scores above. Since it splits between 20 and 21, just as we would with a median, we're going to take the average of that. And so quartile 3 is going to be equal to 20.5. All right, and so now in order for us to find the interquartile range, we're going to subtract quartile 1 value from the quartile 3 value. Notice that we're not getting upper real limits, and that's because these are values in the center of the distribution, not the limits of the distribution. So in order for us to find that, we have 20.5, which is our quartile 3, minus 11, which is our quartile 1, and we get an interquartile range of 9.5. Okay, so in order to show or prove that this is robust against outliers, let's just assume we add a different value, say a value of 32. So now we had 16, now we have 17 values. So that actually changes our quartile 2 to the value 14, right? Because that is the 9th value, so it's the center of our distribution. We then split the lower half in half, right? And we get quartile 1, which falls in the same place between those two 11 values, which gives us a Q1 of 11. Quartile 3 moves up, moves from between 20 and 21 to 21 and 23, and that actually is going to give us a Q3 value of 22. So when we calculate our interquartile range with this new value of 32, we get 22 minus 11, which gives us a range of 11. So where we saw an increase of range of about 30 points, we only see an increase in the interquartile range of about 1.5 points. So it is more robust. Obviously, the disadvantage is that it's only looking at variability within the center of this distribution, so it's not giving us any meaningful estimate of the true variability within that population of scores. All right, so let's talk about then a different method for looking at variability that does take into consideration all of the possible values in the distribution, and that's called the variance. Now, the variance is an estimate of, or it actually is a metric that is the average of the squared differences between each observation and the mean of the distribution. So in this diagram here, I have some data points that I've plotted, and then I have included this red line, which represents the mean of the scores on this y value, this y-axis, right? So the mean is about 2.12, and then each of these represents an individual observation. The arrows are showing the distance from the mean to each of these individual observations. I couldn't put a little arrow here because it's less than, it's a fraction of a point. Now, if we were to take the average of the distances without squaring them, the problem that we would have is if we would have, this one would represent a negative value, roughly about negative a half. This would be a positive value, about positive a half. They'd wipe one another out. We have a positive value of about 1, and then here we have a negative value of about 1, so these two would wipe one another out. So what you would find is that trying to add up or sum the differences between each of these values and the mean would actually give you a value of 0, and you can't square that, so that's not going to be very helpful, right? And so we can't really get an average distance because essentially the sum of all of these differences is going to be equal to 0, which makes sense, right? Because we're calculating based on the mean. So in order to be able to get an estimate of the distance of each of these scores from the mean, we have to square them first, and then we can take the average. Now, because we're thinking about population variances, we're going to use Greek letters to represent that. So we're using sigma squared, and we'll explain why that is the case in a bit. And the formula that we're going to be using is the sum of each individual x value minus the population mean squared, and in order for it to be the average, we divide it by the sample size. So in other words, we would say, okay, so what's the distance of this value from the mean? Let's say it's a half minus a half. We'd square that, which would give us plus 0.25. We've got another one that's minus a half, or is plus a half. We get 0.25. We go on and so forth. This would give us a positive value. We could then add that up and take the average. All right, and this is going to give us sort of an estimate of the average squared difference between each observation and the mean of the distribution. Now, this is helpful, and we'll talk about how to calculate this, and I'll demonstrate that later. But obviously, this is not in the original unit of measurement, and that's why we have the standard deviation. So the standard deviation is essentially the square root of the variance. So you'll see here that this formula here, sum of x minus population mean squared divided by n, is our variance formula. We represent the standard deviation with the Greek letter sigma. Notice it doesn't have a square, right? So sigma squared is our variance, and sigma is our standard deviation because standard deviation is the square root of the variance. Okay, we're pretty clear on that now. And it represents the average distance of each observation from the mean of the distribution expressed in the original unit of measurement. So essentially we get the average squared difference, we then take the square root, and then that tells us what's the average distance of each of the scores from the mean. And so that's what the standard deviation actually tells us. So I'm going to end the lecture here, and then I will finish this part up and do a demonstration of how to calculate the standard deviation.